Hi, everyone. Welcome to my lecture, Machine Learning in Carbon Cycle Research. I'm Yuanyuan Huang, a research scientist in Australia's research agency, CSIRO. In the past several years, I have been using machine learning techniques in my own research on non-biogeochemical cycles centered on non-carbon dynamics. In this lecture, I plan to briefly talk about what is machine learning, some basic types of machine learning algorithms, applications of machine learning in carbon studies or greenhouse gas mitigation, and some examples of machine learning in non-carbon studies. So what is machine learning? Machine learning is a subclass of artificial intelligence in which we enable computers to learn from data, to develop pattern recognition, and to continuously learn and make predictions based on data. Machine learning algorithms normally have a very strong mathematical and statistical basis. You may have already heard the terms like machine learning, artificial neural networks, deep learning, etc. multiple times. I reckon you are all quite excited about machine learning techniques. That's what motivated you to come to this lecture. For different types of machine learning algorithms, we generally separate them into unsupervised learning versus supervised learning two categories. The difference is whether the labeled output variable is involved or not. Unsupervised learning corresponds to inferring underlying patterns from an unlabeled dataset without any reference to labeled outcome or prediction. Clustering is a typical unsupervised learning method, like the right side of the bottom figure. Data points with similar characteristics are automatically grouped together as different clusters. We could use clustering to detect anomalies, to study plant trends, to study the genetic similarities, etc. While supervised learning is defined by the labeled data sets. It's a process of learning a function that maps an input to an output based on example of input-output. It infers a function, or sometimes we create a relationship from labeled training data consisting of a set of training examples. If the training or our target samples use category values, we call this type of task classification. Well, if the target has continuous numerical values, we refer this type of task as regression. So machine learning is actually evolving very, very quickly with a wide range of methods designed to solve different practical issues. I will briefly introduce you two commonly used methodology. One is decision tree-based methods, and the other is the neural network-based methods. A decision tree is a decision support technique that forms a tree-like structure, like here in this one. A decision tree consists of three components. People create a node, a root node, a decision node, and a leaf node. The decision tree algorithm figures out how to divide a training dataset into branches. The branches could be further separated into child branches and so on until a leaf node that could not be separated further. People use entropy, sometimes Gini impurity, or other information gain matrix to split the branches. A high information gain means that a high degree of uncertainty has been removed. Taking the case of predicting whether a customer will buy a mobile phone or not from the lecture of Weissman's as an example, the features or characteristics of the phone forms the base of the decision. The root node and the decision node of the decision represent the features of the phone. The leaf node, that is whether buy or not buy a phone, represents the final output. The main features that determine the choice include the price of the phone, the memory of the phone, and the storage of the phone. After you know what is a decision tree, let's talk about random forest, a commonly used machine learning technique in our area. Random forest is actually made up by multiple decision trees through the following steps. People will normally take the original data sets and create baggage data sets with samples of size n. The number n is smaller than the original size of the data set. Bagging is the terminology used in random forest. It involves using different samples of the training data rather than use just one sample or use all of the samples. After preparing the baggage samples, then people will train a decision tree with each of the baggage data sites as input. During the splitting of the nodes, people don't use all of the features in the data set. Instead, they will randomly pick up a smaller number from all the features in the training data set, then pick the best split using impurity measures like the Gini impurity or entropy. After finishing training of each of the decision tree, people will then aggregate the result of the individual decision tree into a single output. If you are working with a regression task, people will use the average value for each observations produced by each of the decision tree. If you are working with a classification task, people will do a majority voting across all trees for each observations. These steps help to avoid overfitting from one decision tree. A neural network is a series of algorithms that mimic the way the human brain operates to recognize underlying relationships in a data set. Neural networks refer to systems of neurons. A simple neural network includes an input layer, an output layer, and in between, a hidden layer, which performs most of the computations required by our network. The layers are connected through nodes, and these connections form a network, the neural network of interconnected nodes. Neural networks with multiple layers are known as deep networks and are used for deep learning algorithms. Here I took an example from Shapley. Suppose our target here is to make a prediction of the input image among a circle, a square, or a triangle. In our example, our input image is a circle, which is made up by 28 by 28 pixels, that is 784 pixels in total. Each of the pixels are used as an input to the first layer of neurons, here x1 to x784. And each of the neurons is interconnected with a second layer of neurons through the channels. Each of the channels are assigned with a numerical value, for example here 0.8 or 0.2, known as weight. So the input is then multiplied by the weight, and the sum is passed as an input to the second layer. Each of the neurons in the second layer is associated with a numerical value called the Bayes B, which is then added to the input sum. So this value is passed to a threshold function. We call it here the activation function. The result of the activation function determines whether the neuron is activated or not. The activated neuron passes data of the neuron of the next layer over the channels. In this way, data is propagated through the network, which is called forward propagation. In the output layer, the neurons of the highest value determine the output. The value in this example is probability. So for example, in the illustration, the value of square has the highest probability. So square is the predicted output. In this case, we know our input is a circle, but the prediction is a square. So what's wrong here? So what is missing here is the training process we haven't done yet. In the training process, our predicted output is compared against our target. To quantify the errors in the prediction, the computed errors gives us the direction and magnitude of change to reduce the errors. The error information is then transferred back through the networks. The process is called backward propagation. The weights are adjusted accordingly. So the forward propagation and the backward propagation are conducted iteratively until our weights are determined so that the network could predict the target most of the cases. Depending on the complexity of the data, the neural networks may actually take several hours or even several months to train. And it has been used in a lot of complex issues. With the quick advancement of this area, actually there are quite a lot of different variations of neural networks, such as the convolutional neural network, recurrent neural network. Those different neural networks are designed for different computational requirements. If you are interested, there are quite a lot of readings are available online. The application of machine learning in carbon study or greenhouse gas mitigation are widespread and advancing very quickly. You could find machine learning studies in almost every corner of carbon-related science as long as data is an important part of the study. So here I took the figure from Ronick et al. 2022 paper to illustrate how machine learning could be a powerful tool in understanding the carbon cycle and in reducing greenhouse gas emissions and in helping us, the society, to adapt to a changing climate. Machine learning and could be used in precision agriculture, in remote sensing, in monitoring peatland, in estimation carbon stock and fluxes, in forest management, etc. In the industrial sector, machine learning and could be used to reduce greenhouse gas emissions from design to sourcing to manufacturing and to product distribution through, for example, help 3D printing, through optimizing the supply chain, through adaptive control, through detecting greenhouse gas emissions, through optimizing the shipping routes and preventing overstocking of products, etc. Machine learning could and are used in helping us to reduce transportation activities through analyzing and understanding transportation pattern and drivers, through forecasting, through remote sensing, through detecting loading inefficiency, through automating vehicles, and also through understanding the charging patterns and congestion management, etc. I'm sure you could find more examples in different areas where machine learning play an important role. This table synthesizes typical applications of machine learning in greenhouse gas mitigation. These applications tackle issues related to monitoring, budget quantification, upscaling, mapping, optimization, scheduling, management, and forecasting, etc. Topics involving causal inference, computer vision, interpretable models, natural language processing, reinforcement learning, time series analysis, transfer learning, uncertainty quantifications, and unsupervised learning, etc. As you can see, computer vision is by far where machine learning is most widely used in this area. After the broad overview, let's dive into some specific case studies. In the following section, I will talk about using machine learning to quantify carbon fluxes and stocks with examples of mapping and predictions. I will also talk about understanding drivers of carbon cycle relevant processes and improving process-based models through machine learning. In this slide, you see maps of different variables that are critical in non-carbon studies. For example, the gross primary production from flux calm, the above ground biomass, the below ground biomass, and the soil respiration. These maps are generated from machine learning models trained with such level samples. For mapping and upscaling, as shown by the flowchart of flux calm and soil grids, typically, initially we spend quite a lot of time to prepare our samples to standardize our target and also a lot of covariates. In machine learning terminology, a covariate is also called a feature. I have mentioned this several times in previous slides. Covariates are variables that affect or determine the value of our target variable. For gross primary production, for example, covariates could be climate variables, soil conditions, vegetation traits, etc. Depending on our understanding of our targets, we select predictors, features, or in other words, covariates that are relevant to our targets. After feature selection, we then apply machine learning methods to understand the relationship, especially the nonlinear relationship among our predictors and targets. This is what we call model training. And after good model training and satisfactory cross-validation, we then use this trained machine learning model to predict either future or spatial changes of our target. The spatial temporal extent of our prediction depends on the predictors. For example, for flux calm and soil grids, the predictors such as climate variables and more distant products, DM, etc., are global. So we could generate a global prediction of those target variables. To account for the uncertainty of the predictions, normally we use multiple machine learning algorithms, or we use different predictor data sets to generate an ensemble of predictions and estimate uncertainties from those ensemble predictions. To evaluate the performance of the machine learning model, we typically conduct cross-validation. For example, here k-fold cross-validation or leave-one-out cross-validation when the sample size is not too big. In k-fold cross-validation, for example, suppose now our k equals 5. We divided our samples into 5 folds. We used the first, second, third, and fourth fold of the samples to do model training. And we used the fifth fold that is not used in model training to test the performance of our machine learning model. In a second round, we used the first, second, third, and fifth fold of the sample to do machine learning training, and the fourth fold to do model evaluation. We iterate this process 5 times. In this way, we used all samples that are not used in training the model to evaluate the model to avoid overfitting. Machine learning models that performs well on training samples may not good at predicting new samples. So we really need a machine learning model that are good at predicting new samples. So cross-validation is often used to evaluate machine learning model performance. For leave-one-out cross-validation, it takes a similar procedure as the k-fold cross-validation. Here, our k equals the total number of the sample size. As I mentioned, one typical issue in machine learning is overfitting, especially when the sample size is not big enough. For some non-carbon related variables that rely on manual measurements, small sample size is typical. Cross-validation and sometimes careful feature selection, that is, not to use too many irrelevant predictors, in some extent help to avoid overfitting. Autocorrelation, as discussed in this paper I listed in the bottom, and uncertainty quantification are also typical issues that remain to be adequately addressed in many studies. Whether and how autocorrelation should be handled in machine learning-based spatial mapping are widely debated. There are many open questions in making good use of machine learning in non-carbon cycles. One important aspect of machine learning-enabled non-carbon studies is to understand drivers in different non-carbon cycling processes. People use different measures to quantify the relative importance and driver relationship. I took 2 examples here. The bottom left 2 panels shows the relative importance to drivers for the additional carbon sorption potential of soil and equilibrium constant based on a mean increase in node purity, a concept used in tree-based machine learning method, ranked from the top for the most important to the bottom to less important drivers. On the right side of the panel, I took the example in Hoist study on the response and recovery of tropical forest biomass to 2015-16 drought. The red lines in the middle shows the response of a background biomass change during a drought to the top most important drivers. The top first one is soil moisture. If only the middle red line are plotted, we call the plot the partial dependence plot, which shows the marginal effect of one feature have on the predicted outcome of a machine learning model across samples. So actually in a plot, in addition to the red lines, for example, for the response to soil moisture, you actually see a lot of individual black lines. Now the plot becomes individual conditional expectation plot. Each black line refers to one sample or one site if the sample corresponds to site. For each sample, the covariates other than soil moisture are held constant at the set level value. The black line shows for each sample the response of our target to the variations to soil moisture. So as you can see, so we could look into more details from the individual expectation plot compared to the partial dependence plot. Another very handy metric is now Shapley value. Shapley value help to move machine learning from a black box to be explainable. It is a concept borrowed from the cooperative game theory. They are very common and powerful metric that is agnostic to specific machine learning algorithms. By definition, Shapley value is the average marginal contribution of a feature value across all possible coordinations. It may be a little bit abstract. Let me give you an example. So let's say we would like to predict a GPP from 4 features: L temperature, precipitation, photosynthetic active radiation, that's the PAR, and so nitrogen. Suppose from one of our samples, when we have an L temperature of 20 degrees Celsius, precipitation of 500 millimeter, and a PAR of 2000, also nitrogen of 30, our machine learning model predicts a gross primary production of 2 gram carbon per square meter per day. Shapley value answers how much of each of the features contribute to the difference between the prediction of 2 gram carbon per square meter per day to the average of the predictions across all samples, let's say 5. I need to hear the steps on how to calculate the Shapley values. If you are interested in the details, please read the text. I also put here several figures on the right side of the slides. They are typical plots generated from Shapley values. It could give us very detailed information on the contribution of each of the features to each of the samples, like in the top figure and also in the middle left of the figure, or rank the relative importance of features across all samples, like in the bottom left panel of the figure, or the response curve of a target to a specific feature here. In addition to understand drivers, machine learning could be used to improve process-based carbon models in different ways. Here I took 2 examples. One is from Feng's study, in which machine learning is combined with data simulation, process-based models, and big data to improve process-based prediction of soil carbon. Feng will give more detailed explanation in his lecture. A second one is using machine learning to accelerate the spin-up of large-scale process-based models. The idea is, instead of running a global model for spin-up across all global grids, that is very computationally expensive, as you have learned in the course, we train a machine learning model with selected samples to predict the steady state. As you could see from Yang's study with OKD, the performance of the machine learning model at predicting the steady state is actually quite good, with a cross-validation R-square more than 0.8. So instead of running computationally expensive global samples, we now could run only a smaller number of samples with the help of machine learning, which saves us a lot of computational time. I'm sure in the future, there will be more creative ways to combine machine learning algorithms to advance non-carbon studies with your future contribution. So a quick summary. So in this lecture, we talked about what is machine learning and different types of machine learnings, the wide applications of machine learning in monitoring, quantification, in upscaling, mapping, optimization, management, forecasting, etc. We also talked about typical applications of machine learning in non-carbon studies, which include mapping, upscaling, and understanding drivers and improve process-based models. I hope you enjoy the course. Thank you all.